So in this video what we'd like to talk about is acids and bases. This is the first in a multi-part
This will
series on
extend
acids
and build
and
upon
bases.
what we've learned about equilibrium in past videos.
But today what we're going to really focus on are the solution component of acids and bases. We're not necessarily going to really break down the acids and bases themselves, but we're going to assume that they're already in solution, that the solution is already acidic or basic. So you start with what we call the Arrhenius definition. This classifies acids and bases in terms of their behavior in water. So if you say you have an acid, it basically is the substance that will release H plus or hydronium ions when it gets into water. For example, hydrochloric acid is very soluble when it gets in water. It creates the hydronium ion and then the counter ion, the spectator ions left behind. By the same token, if a base is a substance that releases hydroxide ions into water. So sodium hydroxide, if you dissolve it in water, it's going to release hydroxide ions. And just a reminder back here on the acid, sometimes you don't write the hydronium ion as the H3O, you just simply write it as an H+. And just a reminder that these two forms of writing hydronium ions are both interchangeable. So this is your acid. This is what defines an acid and base when it's in water. Alright, so what we usually do is we talk about the pH scale and we say, hey, is the solution acidic or basic? And what that's based on is the hydronium concentration. If you take the negative log of that, you're going to get a pH. And what we tend to say is anywhere from pH 0 all the way to 7, this is considered acidic. Starting out strongly acidic at the very low pHs. As it starts to rise and it's still below 7, that's weakly acidic. If you're right at 7, it's considered neutral. And then as the hydronium ion gets less and less, pH actually raised above 8, 9, and 10, that's weakly basic, and if you have pHs up to 14, that's strongly basic. So this we're familiar with. Something I like to show you in general chemistry too is another form of this is where you actually track the hydroxide concentration, and this follows the same trend. We call it the pOH, which basically is the negative log of the OH concentration in water, and it would follow a similar scale. So now if you're very basic, you would be at pOH at low number, 0. When you're neutral, it's 7. Then when you get up to very high, that means that you have a very low OH concentration. So we'll talk about this more in a bit. Just kind of introduce this H plus concentration and the OH minus concentration. And one of the places it's good to start to review back from General Chemistry 1 is just, can you manipulate these expressions? So if you have the H plus concentration, the hydronium concentration is 0.04 molar, can you turn that into a pH using this equation? What if you're given the pH at 2.3 and you're asked what's the H plus concentration in reverse? So the first one, basically plug and chug, just plug in your concentration, take the negative log of that. So on your calculator you would basically put in negative log of 0.04 and you would get a pH of 1.398, and that's somewhere between pH 1 and pH 2, which you would expect, and we'll explain that here in a minute. But the other thing is if you were going in reverse and you had the pH and you wanted to calculate back H plus concentration, you know the pH, that goes in there. You're solving for H plus, so now let's remember how you undo the log. The common log is you raise it to the power of 10x on both sides. So if you did that to both sides, you would end up getting H plus out, and this would end up being the number 5.01 times 10 to the minus 3. And you should practice this on your own calculator to make sure you know what you're doing there. So here's a chance to practice. And now what we're going to do is it's going to be the same sort of question, but I'm going to work with pOH. And I'm going to let you just practice this on your own. Stop the video. Try this on your own piece of paper, and when you're done and you want to check your answers, restart the video. So let's check your work. If you did this correctly, where you entered 0.065 molar in for the concentration of OH minus, and then you took the minus log of that, you should have come out with the PaOH of 1.19. And then this in reverse, you have the POH, which is 9.45. That enters right here. And so you have to then move the negative sign over to the other side. Raise both sides to the power of 10 to the x. When you're done, you'll end up with an OH concentration of 3.5 times 10 to the minus 10 molar. Alright, so now let's move on to the next concept. And that is, once again, we're focusing on solutions. So, is a solution acidic? And I guess the main point I want to make here is, why do I care? Why do I care about a acidic solution? So I'm just going to make a couple points about acidic and basic solutions. So starting with the acidic one, I think one of the more important aspects of having an acidic solution is that it will solubilize metals. So if you had a metal 0, which would be insoluble in water, if you put it in an acidic solution, it's very common to go through this sort of reaction where you form hydrogen gas, and in the process you oxidize the metal, so it is now water soluble. And we see this happening, unfortunately not on purpose, a lot around old mining sites where there's acidic solutions that actually leach out the metals, and then as the metals go in the solution, it turns the water colored. So this is a mining site outside of Pittsburgh,
Another point I'd make about
Pennsylvania.
acidic solutions is that they're often influential in redox chemistry.
So a lot of oxidation reduction reactions, which consequently is what this was here, but I'm going to give you another example. A lot of oxidation and reduction reactions require that they take place in an acidic environment. And here's a good example that if you were to take copper and you were to react it with hydrochloric acid, it wouldn't react because copper is a very non-active metal, as are many of the precious metals. By the same token, if you took a nitrate ion and put it in the presence of copper solid, no reaction. But if you combine these together, you make the nitrate ion acidic, as in the case of nitric acid, you get this very vicious reaction. There's a picture of it where a copper penny is just literally getting chewed up by this nitric acid, and that particular reaction takes
Changing
place.
the oxidation number of nitrogen from +5 in the nitrate in the reactants over to +4 in the nitrogen dioxide in the products, while the copper started at copper 0 and then it is oxidized to copper 2+ in the products.
And so that redox was driven because it took place in the presence of an acid. So there's just a couple applications, and let's talk about basic solutions. One of the important things is kind of the opposite of what I showed you, and that is hydroxides are quite often used to precipitate metals, and this is real relevant for drinking water cleanup, because if you have heavy metals in the water, which are usually poisonous to us to drink, a lot of times in a water treatment plant they make it slightly basic to precipitate those out. Here's a example. This is that same sort of suspended iron stream coming down. It's suspended in water, and as it comes into this other water area that has a lot of base in it, which is probably naturally occurring weakly basic carbonates, etc., it starts to precipitate and fall out, leaving clean water in its path. And we do this, like I say, in a water treatment plant on purpose. So another reaction is a base is able to neutralize an acid and leave salt and water. This is a chemical spill that released a lot of muriatic acid or hydrochloric acid out on the street, so the hazardous safety people actually neutralized it with a base. And so the net ionic equation that's important there is that a hydronium ion plus one hydroxide just makes water, and this is the neutralization reaction. So I want to review that with you real quick. This is something you learned in General Chemistry 1, but I want you to be sharp on this equation, so we're going to review that before we go into this section. Here's an example of this. This is what I consider to be a little better equation. A lot of people just do molarity times volume equals molarity times volume. I like to put in this little prefix here that represents the subscript of the acid or base, and let me show you what I mean. In this question, how many mils of 5 molar sulfuric acid is needed to neutralize 37 mils of 7 molar barium hydroxide? So here's the balanced chemical equation. Alright, but we're going to just set it up with this equation and basically plug and chug. And look what we did here. This is sulfuric acid, so there's 2 equivalents of acid for every mole of sulfuric acid that's actually in solution. So consequently, I use that number, and that SA is the subscript of the acid. And so it's 5 molar, and the volume I'm going to use is the unknown. And then I get over here and look at the base, and it looks like it also has a 2 for the subscript. So when I set that up, I include that 2 right there, times the 7 molar, 37 mils, and then basically I just collect the terms over to the right and solve for VA. So now, why don't you practice using that equation? How many mils of 4 molar sodium hydroxide to neutralize 25 mils of 2 molar HCl? And then the second problem is how many liters of 3 molar phosphoric acid would neutralize 75 liters of 6 molar barium hydroxide? So here you go. Stop your video, try this on your own paper, and when you're ready to check your work, you can restart the video. Okay, let's review the first problem. Pretty straightforward, and you'll notice there's no subscripts in here because the sodium hydroxide and the HCl, neither one have multiple hydronium ions or multiple hydroxides. So you just basically plug and chug. You don't need the subscripts. Solve for VB. Should have got 12.5. And one of the keys here is when you bring this molarity over, it's going to cancel. It's going to leave the volume. So the final volume is whatever volume I used here. So it's in milliliters. So now you can set this one up the same way, except in this case it's phosphoric acid. And if you look at the formula for phosphoric acid, it's H3PO4. So there's actually 3 protons in every mole of phosphoric acid. And by the same token, barium hydroxide has 2 hydroxides. So consequently, that 2 goes into this formula, and the 3 from the phosphoric acid goes into this formula. Plug and chug, and you end up with 100 liters. And once again, I entered liters. When I solved and collect terms, I'm left with liters, and that's correct for this problem. So once again, is the solution acidic or basic? It's the pH scale. That's what we work on. What I like to show people is just to understand that basically when you start off at pH 0, that means that you actually have, if you were to solve it in reverse, you actually have 1 molar hydronium ion concentration, which just, if I was doing it by the power of 10, that's 10 to the 0 power. So now if I just move the slider bar over to a little higher pH and get to pH 2, and then I plugged in the pH 2 and solved for a hydronium ion, I'd end up, okay, it's 0.01 molar, which if I express that in the power of 10, it would be 10 to the minus 2 power, which consequently, if I take the log of that, is 2. So you see the trend here. When you get over to 7, you can imagine that I've moved the decimal over 7 times. So if I do the pH of that, it's going to be pH 7. And etc., etc. Even when you get up to pH 12, it's 10 to the minus 12. I've moved the decimal over 12 times. Alright. But once again, as I showed you earlier, there's another measure, which is the measure of the hydroxide ion at any time. But you might be thinking about this and go, well, wait a second, if it's highly acidic, is there, if I just added HCl, is there any hydroxide whatsoever? And the truth of the matter is, if it was measured at pH 0 or pH 2, there would be some small amount of hydroxide present. And in fact, if you'll look at the trend, when you're at pH 2, the hydroxide ion is 10 to the minus 12, or the POH would be 12. And when you're at pH of 7, the POH would actually be 7. And when you're at pH of 12, the POH would be 2. And so look at the trend, and this is where we're going next. If you sum up pH plus POH all the way through, in the first case 2 plus 12 is 14. When you get here, 7 plus 7 is 14. And when you get here, 12 plus 2 is 14. So the question kind of rises, what is that trend, or where's that coming from? And so I'd like to talk to you about the autoionization of water. That basically when you take water, it has a very slight equilibrium towards dissociating into protons and hydroxide ions. But we know that's very light, right? Because water isn't acidic nor basic. In fact, if you were to solve for the Kw, or basically set up the equilibrium expression at 25 degrees C, we know that K is 1 times 10 to the minus 14, and that confirms what we thought, and that was that this number should be very low, so it favors staying back to the reactant side. Okay? But there's the magic number. There's where that 14's coming from. So just think about water if it's sitting right there and you let it settle out, right? Then that would mean that there is an equal number of H pluses and OHs form, and what we learn from our equilibrium is, so that's unknown, and that could be considered x squared equals 1 times 10 to the minus 14. Now if you were to solve for that x and get it out of there, you'd basically see, that H plus concentration and the OH concentration at in neutral water is 1 times 10 to the minus 7. And that we knew because we know that when it's water at equilibrium, it settles into a pH of 7 or a POH of 7. But here's that relationship, that whatever the H plus is, there's a corresponding OH, which if you multiply them together, they equal 1 times 10 to the minus 14. Or as we saw in the previous slide, if you did it in terms of pH plus OH, it would sum up to 14. All right, and this is going to help you solve a lot of problems. You just need to keep in mind that even though there's a very strong acid present, there's some slight amount of base, and those combine together in such a way that you fulfill this equilibrium expression for water. So let me kind of give you a couple examples of that. All right, so we set up water at equilibrium. Everything's happy here. And now we drop in 4 molar HCl. And we remember from Le Chatelier that if you're increasing the H plus concentration, that's going to start to work on the product side of this. And so he's going to, by relieving the stress, it's going to shift back to reactants, right? And by doing that, it's going to actually consume up the hydroxide. All right? Now, if we were to solve that, all we have to do is, in this case, we don't have to set up a reaction table. We know that HCl completely ionizes, so the nice thing with the strong acid or strong base, you can drop that concentration directly into the equilibrium expression for water. And so in this case, we're going to drop the 4 mole right in there, and we're going to solve for hydroxide. And we find out the hydroxide is indeed very small. It's 2.5 times 10 to the minus 15. And that's what had to happen. It had to shift and become much smaller to consume the extra H plus that was added in there. All right. So when it comes to calculating the pH right now, though, we basically can look right here and say, well, it's 4 molar HCl. That is the H plus concentration. If I want to figure out the POH at this moment, then I have to set it up into this water autoionization expression. All right, set it up into the Kw for water. and then just solve for the OH, and you basically would have 2.5 times 10 to the minus 15th, which you could take the minus log of that and actually get the POH. Okay, so now let's do the opposite. We get water, let it settle into equilibrium. Now we're going to drop strong base in there. Same thing happens. The base is actually going to build up the hydroxide products. So Le Chatelier would say, well, I predict that it's going to shift to the left to consume some of that excess of hydroxide, and consequently the H plus is going to start to drop. The way you can solve this is set it up in an equilibrium expression. It's a strong base, so all of that hydroxide is considered to go into the solution. Now you just solve for the unknown H plus concentration, and you see that it is indeed very small, 5 times 10 to the minus 15. Remember, it started at 1 times 10 to the minus 7, and now it ended up at 5 times 10 to the minus 15. And once again, if you wanted to find the pH of that, you could take the minus log of that, or if you want to find the POH, find the minus log of that. So this is kind of the end game here that I want you to get very used to doing when you work with water solutions, is if you know some acidic component, you can figure out the proton concentration, but immediately then you should know the resulting OH concentration, and that is because this concentration, if you're talking in terms of concentration now, that concentration times that concentration will always equal 1 times 10 to the minus 14th. And this is just an example. Anywhere in the basic zone, even if it's slightly basic or weakly basic, 1 times 10 to the minus 10, if you multiplied those two together, you'd still end up with 1 times 10 to the minus 14th. And now if you did it from the pH point of view, remember these are powers, so when you're multiplying powers, it's the same as adding, right? So basically, pH plus POH will always equal 14 no matter what the concentration is. And just keep that in mind so you can always find that third part. So let's practice that a little bit. I have a research chemist. He had 3 times 10 to the minus 4 molar HCl. So now let's see if we can calculate the OH minus concentration. Let's figure out if the solution is neutral, acidic, or basic. Figure out what the new pH is, and also figure out what the POH is. So when you can kind of calculate all 4 of these things together, you're right where you need to be from this section. Okay? So you might want to stop the video and work on this, see if you can get your answers, and when you're done working, then start the video again and you can check your work. So let's see how you did. Let's calculate the OH minus first. Alright? Okay, remember what we had learned earlier, that really if I have hydronium concentration, I want to find the OH, always go to this expression for water. That's the easy way to solve this. And we know that those multiplied together should equal 1 times 10 to the minus 14. So you just plug and chug, solve, and you end up with 3.3 times 10 to the minus 11. Okay, is the solution acidic, neutral, or basic? Well, if you're pumping in acid to this concentration, 3 times 10 to the minus 4, and you know that these two together have to multiply up to 1 times 10 to the minus 14th, and this one's much smaller, it must be acidic. Next question, what's the pH? Well, the pH is fairly simple because remember it's a strong acid. So you basically take that, assume that all of that acid becomes hydronium ions and chloride ions. And so if you take the negative log of this, you'll end up with the pH of 3.5. What's the POH? Well, there's a couple ways you can do this. One is you could take the OH minus concentration, take the negative log of that. But also don't forget that POH to pH relationship, right? That those always sum to 14. So if I knew what the pH was, I could subtract that from 14, and I'm always going to have my POH, and vice versa. All right? So here's one more opportunity for you to practice. calculate the hydronium ion concentration, pH, OH minus concentration, POH for each of these solutions. One's a strong acid and one's a strong base. And I just want to caution you, these techniques we're learning are going to be relevant to weaken acids and bases, but we're going to have to do some caveats with that to get this correct. But let's just work on this right now. Stop your video. When you get your answers, then you can restart your video and check your work. Okay, starting with the strong acid, dissociates completely. That's what you always assume with the strong acid. Likewise, that's a strong base, so it's going to dissociate completely. And then we're going to be able to solve using what we know. So let's move up here and work on the acid first. Okay, so hydronium ion concentration, if it's 0.3 molar nitric acid or strong acid, all of that becomes hydronium ion concentration. The pH is very simple. Just take the negative log of this. It ends up being 0.52. The OH is, you can always use that relationship for the equilibrium expression for water. Okay. Solve, and you end up with 3.3 times 10 to the minus 14th. The POH, you can end up solving, but I think the easiest way is, look, if you know the pH, subtract that from 14 and you'll end up with the POH. And in the second problem, you're calculating for the values of calcium hydroxide. It's a strong base, strong electrolyte as it says here. So you can assume that all of this becomes base. The one catch is, though, it's calcium hydroxide, so for every mole of calcium hydroxide that disassociates, you get 2 moles of hydroxide ions. So you do have to kind of watch for that little guy. Take the minus log of that, that's going to be your POH. If you want to find out your H3O concentration, there's a couple ways of doing it. One is you could multiply this by X to equal 1 times 10 to the minus 14, which is what they've set up here. Solve for that. When you get down here and want to find the pH, once again, I always suggest if you know the POH, subtract it from 14. That's going to be your hydronium ion concentration. In this case, they just knew the H3O plus concentration, took the negative log of that, and you'll end up with the same answer. So strong acids and strong bases. You know, just like we talked about, a strong acid completely dissociates in water, and that's going to lead us to many assumptions that we used just now to solve a lot of these calculations. Basically what we're saying here is that the Kc is in essence much greater than 1. So if you want to find the H3O concentration of a 4 molar HCl solution, you can just assume that all that H plus is disassociated, and so the concentration is 4 molar. Strong base completely dissociates in water. Long story short, if you want to find the concentration of a 4 molar strong base solution, it is at 4 molar. The only catch on both of these is if these are diprotic or they're dibasic or tribasic, you just have to account for the extra equivalence like we did in the last problem. And so I'm just going to show you some common acids and bases. I've got acetic acid or vinegar, citric acid or lemon juice, vitamin C, ascorbic acid, some aluminum salts that show up in baking powder. And here's another commonly used acid. This is muriatic acid or a hydrochloric acid. And the thing is this muriatic acid is a very strong acid. It fully dissociates. But obviously, we are able to eat this stuff so it doesn't fully dissociate, right? And consequently, we get down to the base section and we have the same situation. We have sodium hydroxide, lye, which is used in oven cleaner, ammonia, which is a weak base, and sodium carbonate, which is a weak base, and sodium bicarbonate, which is also used in baking powder. These are obviously not very strong bases. because we consume those all the time. So an example of the weak acid would be vinegar, which, like I say, doesn't fully dissociate. Thus is safe to consume. And an example of the weak base would be the sodium bicarb, or baking soda, which we also can consume. So my point in showing you this slide is there's more to the story. What we've talked about today, strong acids and strong bases, and I used it mostly to highlight how you can figure out some solution calculations. So in the next videos, we're going to have to talk about some weak acids and bases, and we're also going to have to talk about how you characterize those particular materials as opposed to just characterizing the solution. So I hope this has helped, and I hope you're very confident doing some calculations with solutions in regards to acids and bases.